Hello. Today I'm going to talk about stepper motors. This is a stepper motor. For this one, I took off the lid so you can look inside. In Japanese, it's called a stepping motor, by the way. Japanese people should be careful not to say stepper motor when you have a technical discussion in English because it probably won't be understood. First, let's take a look at the structure of the stepper motor. I'll pull out the rotor. A stepper motor consists of two parts. This is a rotor, and this is a stator. Let's have a closer look at the stator. A stator is made of an iron core and coils. If you have a closer look, you can see the iron core has grooves on the inside. These grooves are called teeth. The teeth play a very important role in stepper motors. Another component that consists of a stator is these wound wires. They are called coils. The rotor of a motor rotates when a current passes through these coils. This motor is a two-phase stepper motor. This stepper motor has 8 coils in total. 4 of them belong to phase A, and the rest 4 belong to phase B. This motor has 2 phases. That's why it's called a two-phase stepper motor. Next, this is a rotor. The rotor has teeth on it, just like the ones on the stator we saw earlier. There is a magnet inside this rotor. The parts with teeth are called rotor cups. The rotor cups cover the magnet. I illustrated the structure of a rotor. A rotor consists of a magnet and rotor cups. This is a cylindrical shaped magnet. It has a north pole and a south pole. Then, the rotor cups with teeth are put on it. That's the structure of a rotor. As the 2D picture is difficult to understand, I drew another one in 3D. The cylindrical magnet is covered by rotor cups with teeth. The rotor cups are like lids. Look at how the teeth on the rotor are aligned. Can you see how they are aligned alternately on each rotor cup? These pictures illustrate how the rotor looks from above and from the shaft. First, let's look at the rotor from above. This figure illustrates what it looks like. The inside of the rotor is made of a magnet, and the rotor cups cover the magnet. Naturally, the rotor cups are magnetized. The teeth are aligned alternately on each rotor cup. The rotor cup on the North Pole side is magnetized to the North Pole. As the red parts in the illustration shows, the teeth on the left rotor cup are magnetized to the North Pole. The same thing goes for the other rotor cup. The teeth on the right rotor cup are magnetized to the South Pole as in the blue parts. And the North and South Pole teeth are arranged alternately. The right figure is the view from the shaft. The left figure is the view from this direction, but this time we'll look at the rotor from this direction. When viewed from the shaft, the North Pole and the South Pole are alternately arranged. Of course, the teeth magnetized to one pole is in front, and the teeth magnetized to the other pole is in the back, but from this direction it looks like they are alternately arranged. 2 rotor cups cover the magnet. There are 50 teeth on each rotor cup. Then how many magnetic poles are there on this rotor? There are 50 teeth on each rotor cup, and they are arranged alternately. So when viewed from the shaft, it would look like the rotor has 100 poles. I added an illustration of the stator here. The stator also has teeth. When a current is passed through the coil in the stator phase works like electromagnet and attracts the rotor teeth to the stator teeth. That's how the rotor rotates. This phase can be phase A or B. Depending on which phase the current flows through and which direction the current flows, the direction of the rotor rotation and the step angle are determined. So this is the mechanism of how a stepper motor rotates. Then, what is good about stepper motors? One of its advantages is that the step angle is determined by the structure of the rotor and stator. I'll explain the details later in this video, but a stepper motor can rotate to the required angle without this encoder, which is essential for servo motors. Stepper motors can do it in an open loop without using a feedback loop. By the way, there are several types of stepper motors that have different structures. One of the types is called PM type. A permanent magnet is used as the rotor, no rotor cups. This type of motor rotates the rotor using the magnetic torque of the stator and rotor. This type of motor has a disadvantage that it cannot have small step angles because the rotor cannot be magnetized with a large number of magnetic poles. Next is the VR type. It utilizes reluctance torque. These are stator iron cores, and the rotor is also made of iron core. No magnets are used. In terms of the type of motor, it might be better to categorize this VR type as a switched reluctance motor rather than a stepper motor. It might be better to say that a switched reluctance motor can be used as a stepper motor. The stepper motor I introduced today is a hybrid type. This PM type magnet torque and this VR type reluctance torque are combined. This rotor contains a magnet. The magnet is covered with rotor cups or iron core. That's the structure of a hybrid stepper motor. Now let's try to actually rotate the stepper motor. This stepper motor has 8 coils. 4 of them are phase A coils and the other 4 are phase B coils. This is a 2-phase motor. The coils for phase A and B are placed alternately at 45 degrees from each other. The phase A coils are located here, 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 and here. The phase B coils are the tilted ones. They are located here, 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 and here. Now let's pass current through the phase A and B coils to rotate the stepper motor. I'll start passing current to the phase A coils. Take a good look at this rotor. Let's start. Did you notice that it rotated a little? Next, I'll pass current to phase B. The rotor rotated a little again. Next, let's change the direction of the current. When current flows through phase A, the rotor rotates little by little clockwise. I'll apply current to phase B. I'll change the direction of the current and apply it to phase A and B. Change the current direction again and apply it to phase A and B. You can see that the rotor is rotating little by little. As I've been saying, a stepper motor rotates by combining a rotor, a stator, and their teeth. By passing current to either phase A or B coils in the stator and changing the directions of the current that flows through the coils, the motor rotates the rotor. By the way, the operating principle of stepper motors and how to drive them are explained in details in the technical articles released by Oriental Motor and on the Rome website. If you want to know more, I recommend to have a look. The links are in the description. A stepper motor can be used on its own. However, it's usually used with a motor driver, like this one that controls the current applied to the motor. Earlier, I was passing current to the phase A and B coils manually, but this motor driver handles such control automatically. I connected the motor driver to the stepper motor. The setup is done. This motor driver rotates the stepper motor by 1.8 degrees when it receives one pulse. When you input 10 pulses, for example, it rotates the stepper motor by 18 degrees. Now let's try applying 1 Hz pulses. Let's start. Can you see that the stepper motor is rotating at 1.8 degrees per second? I'll increase the frequency. The vibration is quite strong. The vibration is strong because I haven't implemented microstepping. I am currently applying 200 Hz pulses to the motor driver. So this stepper motor rotates once per second. 1.8 degrees by 200 equals to 360 degrees. I'm applying current to the stepper motor. The current running through the phase A coils of the stepper motor is displayed here. The current of phase, it changes polarity between positive and negative. In other words, the direction of the current flowing through the coil changes depending on the state of rotation. A current also flows through phase B, but the current flowing through phase B has a different current phase. I remember that the current of phase B is delayed by about 90 degrees compared to phase A. The stepper motor is rotating now, but I'm going to stop the rotation. Now it's stopped. The stepper motor is not rotating, but the current is still flowing. This is because a current is passed through the stator to hold the shaft so it doesn't rotate. The shaft will not rotate unless you apply a lot of force. The current is still flowing even when the rotation of the stepper motor is stopped. Next, I'll increase the rotation speed. In other words, I'll increase the pulse frequency. I'm increasing the frequency more and more. Take a look at the current waveform. The current waveform has an obtuse angle compared to earlier. This is because the coils in stepper motor have inductance. The torque of a stepper motor is generally proportional to the current. The larger the current amplitude, the higher the torque. As the rotation speed increases, the current waveform angle becomes obtuse, which means the torque becomes lower. Therefore, the torque of a stepper motor is lower at high speeds. On the contrary, torque is highest at low speeds. That's the characteristics of a stepper motor. We've been rotating the motor by 1.8 degrees per pulse, but there is a stepper motor controlling method called microstepping. Now I'll give it a try. Now microstepping is implemented. The waveform was square earlier, but after implementing microstepping, it became a sine wave. Can you see the difference? Microstepping is a control method of stepper motors that divides the pulses into smaller parts. The motor was rotating at 1.8 degrees per pulse, but by applying microstepping, the step angle becomes finer. I decreased the number of poles in the illustration to make it easier to explain microstepping. This is the rotor and these are the stator coils A and B, phase A and phase B. First, current is passed through phase A. Let's say 1 amps is passed, and let's say 0 amps is passed through phase B. This will create a magnetic flux in the coil for phase A, so the rotor doesn't rotate. Suppose you want to rotate the rotor by 90 degrees. What do you need to do? Set the current flowing through phase A to 0 amps, and then set the current flowing through phase B to 1 amps. Then the magnetic flux in phase A disappears and a magnetic flux is made in phase B. When this happens, the rotor rotates clockwise according to the magnetic flux. This is how the rotor was rotating before implementing microstepping. So what is microstepping? The rotor was rotating 90 degrees per pulse. Let's say you want to make it 45 degrees per pulse. What you need to do is to reduce the 1 amps that was initially flowing through coil A to 1 over square root of 2 amps and pass 1 over square root of 2 amps to coil B as well. This will generate magnetic fluxes in both coil A and coil B. What happens when you combine these magnetic fluxes? A magnetic flux of length 1 is generated in this diagonal direction. Previously, the rotor only rotated 90 degrees, but now it rotates 45 degrees to the half. What if you want to rotate it in even finer increments, like 30 degrees? This is 1 amps and this is 0 amps. Make this current half the square root of 3 amps and make the current in coil B 1/2 amps. Then, the combined magnetic flux current is the square root of half the square root of 3 squared plus 1/2 squared, which is 1. The combined magnetic flux points in the 30 degrees direction. So the rotor rotates by 30 degrees. Let me sum up what I've been saying about microstepping. Microstepping is a controlling method of stepping motors that finely increments the rotation angle of the rotor. It's achieved by controlling the ratio of the current that flows through these phase A and B coils and the amplitude of the current. Then how is microstepping controlled in a circuit? This is the motor driver. It contains 2 full bridge circuits. There is a switch here. This is a power semiconductor. The power semiconductor uses a control method called PWM to control the current that flows through phase A and phase B. Now, let's look at the differences between normal control and microstepping. With normal control, the stepper motor moves in a jerky manner, not a very smooth move. However, the one with microstepping is moving quite smoothly. There is no jerkiness at all. Microstepping is a control method to increment the step angle. If you increment the step angle and make the step angle smaller, the resolution becomes higher. Now, what is good about stepper motors? Stepper motors can control the step angle in an open loop. Moreover, it doesn't need an encoder to control the rotation angle. A stepper motor rotates the rotor by an angle determined by the structure of the stepper motor. Due to this characteristic, stepping motors are used in conveyors and factories and motion control that doesn't require that much precision. They are often used in 3D printers. Another advantage of stepper motors is the reasonable price. They have a simple structure without precision parts like encoders. That is why the price is low. However, stepper motors sometimes lose steps. When the load exceeds the motor's holding torque capacity, the motor loses steps, which means the motor's position deviates. What is worse, they cannot detect step losses because they operate in open loop. But some stepper motors have encoders apparently. I prepared a servo motor here. This is a disassembled 1.5 kilowatt servo motor made by Yasukawa Electric Corporation. This is the rotor. The rotor has an iron core in it, and permanent magnet is attached on the surface. The structure is quite different from this stepper motor. And this is the stator. The structure is basically the same as permanent magnet synchronous motors. This is the encoder attached to the servo motor. By using this encoder, it becomes possible to control the rotation angle with high precision. That's why servo motors are often used for precision control. Servo motors contain precision parts like this encoder, so their prices are a bit higher compared to the prices of stepper motors. Today I explained about the basic principles of stepper motor operation. It was a brief explanation, but I believe you were able to grasp how stepper motors work. Thank you for watching.